All right, I guess I'm going to get started. I'm Bart Smith. I'm one of the co-leads for the SI subsystem, and today I'm going to be talking about an overview of our SI subsystem and algorithm. If you'd like to ask questions, you can. We also have some time at the end. First, what is stereoscopic imaging? Stereoscopic imaging is a subsystem that will have our cameras would take pictures and this is set. We're going to use those to get information about where that is at, so we can send that information to the GNC subsystem. That way they can navigate around that. Then we also have, we're going to download those photos, and then we're going to be able to recreate Mississat in 3D afterwards. So this is an overview of the subsystem algorithm process. So you can see here it starts with the capturing images. Then we're going to go to feature detection, feature extraction, feature matching, feature pair selection, RSO tracking, and then back to images again. So that's going to run, repeatedly for each image. It's going to go back through that process again. And this is done using a few different open source algorithms that we combined. We use feature accelerated segment test, which is fast. The speeded up robust features, which is also called SURF, and the fast approximate nearest neighbor search library, also called FLAN. I'm going to use those short versions throughout the rest of the presentation.
That'll be a quiz at the end, right?
Yeah.
Yeah.
All right, so the first step is to capture the images. These are, so you have two cameras, they take those simultaneously, and we take images at a rate of 2 pairs per second. After we have the images, we go to feature detection. So this is using the FAST algorithm. We're going to do 2 tests to determine if something is a feature. What this is doing is going to test for corners, because this is the fastest way we can find our object. All these tests are done by comparing the pixel intensity based on a certain given threshold that's going to be different. The first step, we're going to look at 4 pixels, specifically pixels number 1, 5, 9, and 13 on this picture here. We're going to make tests and see if 2 consecutive pixels meet that threshold of difference in intensity. So they're that much lighter or darker. If that step is passed, we're going to go to our second step, which is where we look at all 16 pixels that are boxed on that picture. Then we have, for that step to pass, we have to have 9 consecutive pixels pass the test. After a feature is detected, we're going to extract some information about that using SURF. SURF basically collects some identifying information about the feature, like intensity, stuff that we can use to find it again if we're comparing images later. So after we have the feature detected and we have some information about them extracted, we're going to go to feature matching. So using stuff we got from SURF, FLAN is going to take that information and pair up our left and right images. So they're going to see if they can, each image is going to have the same feature in there. They're going to match those up. FLAN, although it's very fast, but it's also not super accurate. So sometimes we'll have mismatched pairs, other things in the background that'll be matched up when they shouldn't. So to eliminate this, a custom function was used to eliminate inappropriate pairs. So this is going to eliminate any matches that are outside of a certain radius from one of the features. So you can see here on these pictures, on the one on the left has a couple of lines going down to the bottom where something isn't there. These are features that are paired up that shouldn't have been. So after using this custom function, those are eliminated and we get the 2 features matched up that should be. So after we have all our features verified, we're going to go into RSO tracking. First step in this is to calculate the geometric center of Mississat. The center is approximated by calculating the average of all the values in the X and Y dimensions. The X and Y is like the camera pointing outwards, Z is going out from the camera, X to the right, and Y up. Then after we have the geometric center approximated, we're going to calculate our alpha and beta angles. These are used by the GNC subsystem and what we'll be sending afterwards. So how these are calculated, we have these equations here. We have the field of view along the relevant axis, which is the one on the top left. Alpha is in the X direction, beta is in the Y direction. Then we have the coordinate for the geometric center. And then that is over the number of pixels along that dimension. And this is done for each image. So we will be sending 4 angles to GNC for every image pair that we have. So after we get all this information and send it over, we're also going to save the images. So we've saved the pairs. We don't save like all the images, only the ones that have been matched up and verified. And also to reduce our storage, we're going to crop all of our images around the geometric center. They end up with an 80 by 80 size, which saves about 99% of our pixel space. Then, like I said before, after the images are sent back down here to Earth, they're going to be put into a program to create a 3D model. Some other parts of our system that aren't part of the algorithm, we have our camera baffles. This is to help reduce the sun glare, which if you take photos, you know it can be a problem here on Earth. In space, it's a lot worse because we have the atmosphere. So we have these custom baffles. This here is our schematic. This side here on the left is going to be with our camera lens, and that's going to go out on the larger opening there. Right now we have some plastic baffles that were 3D printed. We do have plans to get some new aluminum ones. And then testing is a big part of the SI subsystem right now. And it can be hard to find a good area for this because we need a few different things. We have to have our Mississat model, our camera setup that's able to run the algorithm. We have a spotlight, a pretty big stand that we have Mississat set up on. We also can't have a lot of sources of light, and we also need to have a source of power for all this stuff to run. So after we get everything set up in a suitable location, we're going to have Mississat set up on our stand. We're going to have our cameras pointed at her. Then we will have our spotlight in different locations around the area, pointing at Mississat to variate, to simulate different sun positions. Then some frequently asked questions. What if the cameras are going to point at the sun? Well, hopefully, because the GNC algorithm is supposed to avoid this, so it should never happen. But if it does somehow occur, the cameras are going to automatically shut off so they don't get damaged by the sun. Then on the other side of this, if we're where it's completely dark, the sun's blocked out. If it's too dark, the GNC algorithm is going to propagate Mississat's position until we're able to get a good picture again. There's also a chance that light reflecting from the moon could give us enough light to see Mississat, but we're not going to be able to know till we're in space, unfortunately. I went through that really fast, but I'm happy to go over any questions. Yeah, Colin.
What
fascinating subsystem. How could an intrepid young engineer get involved with SI? Such as, is there like a meeting time every week?
We do have a meeting time every week. It's gonna be at 4:30s and every Thursday
That
in
is
the
so
Sat
fun.
Lab. You can also reach out to me or Colin.
Ooh, I like those guys.
What is it coded in the algorithm?
C++. If you want to look at the algorithm, it's on GitLab. There's a README to explain how to build it and run it on the drive as well.
I guess have like a theoretical max operating range, because
Not to my knowledge. It is, so in our testing, we need to try and find an area that is clear of background obstacles for like at least 100 meters, so 300 feet or so. The goal is to stay within 10 meters of Mrs. Sat. If she gets too much further away, we're not going to have the fuel to be able to keep up with her. So I'm not positive if we have a max, but too much further than 10 meters and we're not getting there.
For our mission, but it would be good to know.
yeah, like the visual on the side, like, assuming you didn't have a little bit of it.
Yeah, and it would be good to know what the maximum range of our SI system is, or better yet, what the maximum and minimum ranges are as a function of, say, camera baseline, as well as camera hardware and specifications. Those could all be PIR and CERT questions that we might have to field someday. That would show relevance, not just our mission, but to scale up our Mr. Mrs. Sat experiment.
Yeah,
Could your algorithm detect orbit decay?
detect orbit decay. I don't think so. We're mostly seeing over those alpha and beta angles, which are used by the GNCs. I don't know enough about that stuff to tell what all they can get from that. I'm not sure if Colin or Dr. P knows.
Not on a long enough time scale. So,
What was the question? What does GNC do with it?
If the algorithm could detect orbit decay, necessary.
Oh,
because the cameras are also on kind of a moving frame of reference, it would be a challenge, because we're also being slowed down in our orbit. But yeah, if you had, I suppose if you had, because we're getting GPS data from Mrs. Sat, but if we had something that we weren't getting GPS data from, if we knew the location of our observer, and then these cameras, because they can tell us where the target is relative to the observer, so we can kind of over a longer period of time deduce what its orbit is relative to ours. That's probably not the most efficient way of determining that.
it's not exactly orbit decay, but at the end of the mission, when Mr. starts running out of propellant, they'll naturally drift apart. Because Mr. has will have a lot more drag on him than Mrs. will. So if things are going spectacularly well at that point, the data and the images, right, should show the range increasing to whatever the limit is of the SI system. Assuming that Mr. Sat holds attitude control and is pointed at Mrs. Sat. Flat is there. That would be like a fully, gloriously successful mission if we got to that point.
Which I don't know if it's even, because I think right when we finish circumnavigation, we just point into our downlink orientation. So I don't even know if we linger on Mrs. Sat.
I guess, well, yes, it would depend on exactly how ConOps are written at that point, what the exit criteria are.
Yeah.
So Mr. Sat like tracked in Sat, right? So on the dark side, when you're propagating it, what happens when like it's the light side and it's not there? Does it just like start looking in random directions? You just hope it works.
I only know what the cameras do. I don't know how we change our position to look for Mrs. Sat.
To my knowledge, we do not look for Mrs. Sat. If she's not in our field of view, The system will keep running, throughout the whole mission, or like from when we started until downlink, and so, we can, you know, as Mr. Sat maintains attitude, if he does suddenly get sight of Mrs. Sat, if she's not where we expected her to be, then we can latch back onto it and pick up from there. But
This might be a Donna question, but we could, with, the last knowledge of Mrs. orbit or current orbit, we could propagate forward Mr. and Mrs. orbits, and then the GNC system could, with propellant left over, could do maneuvers to both close the range as much as possible, as well as maintain an attitude pointed toward Mrs. But yeah, but I don't know exactly how the GNC concepts are written. That would hurt.
I think every subsystem should do this. This is very good, like,
Any other questions?
When we find another gray object in space.
I believe it could detect that as Mrs. Sat. We should be able to, you know, if we're staying close enough, like we're supposed to, like Colin said, we should be focused enough on Mrs. Sat that any other gray objects would get pruned out for custom function because they would be too far away.
Yeah, that's where the stereoscopic side comes in, because you have these two cameras that are taking images of the same view, but very slightly different. Objects that are closer to it are going to be more different looking than like the moon. The moon's gonna look the same in both images, and so that's gonna get filtered out by the algorithm. Whereas up close object, we're not.
And space is crowded, but it's not that crowded. So that scenario is pretty unlikely, because if there were that object, it's probably going to be moving pretty fast relative to Mr. Sat. So it'd probably go through his field of view pretty quickly and not get detected long term. But if by some miracle he did lock on to somebody that's not Mrs. Sat, that would actually be pretty cool and pretty interesting. And we really want to see the images in that case, right? Trying to figure out what in fact it was. And kind of flag it down on the side.
Best possible demonstration of technology. Sorry, like we accidentally imaged like classified airport things, I'll go to jail.
You mentioned the sampling rate was two pairs of images every second,
Yes.
right? How long does it take? So when you get a pair of images, how long does it take the code to then calculate and send the alpha beta angles to GNC?
I didn't find a specific time, but based on our testing, it's like a few seconds. Yeah, that's
They're pretty speedy algorithms, I know.
But does it happen before the next pair of images comes in? Does it stay ahead of the inflow?
That is, I don't know.
That'd be another good piece of information to have to figure out. Because that sampling rate could be useless if it's overloading the system. It could corrupt the results.
Sure.
The was it Flan that had the custom algorithm to get rid of the outlet, the misidentified?
Oh, this the way I read it was after plan, we have our own.
Yes.
Yeah.
Was that written by an MSAT number?
I believe so, yeah. That's how I read the documents.
Okay, do you know who it was by chance?
I do not.
Oh, I have a guess, but I'm guessing it was Alex. I was just curious. Bart, tell us what's left. So Colin made a, very vague, thinly veiled reference to recruiting SI members. Wasn't very obvious about it. But what's left for SI to do? What's going on right now?
SI right now is really focused on the ground testing. Hopefully we're gonna do spotlight soon. We can go back on that. Then we also need to figure out our thermal problem with our cameras in the vacuum. We also need to get our new baffle made. It's going to be the aluminum ones.
And where was SI before you guys took over this fall? with Simeon's testing, what had been done and then now what's left to do to complete that ground testing.
I believe they've covered the baffle testing, the lights. But they want to redo it again once we get the new baffles. Then
But they did outdoor testing with the stand that he built, right? How far did that proceed and what's left to be done with that?
I don't know, I couldn't find any documentation about what happened there when I was looking this up.
Yeah, a lot of the testing documentation is not super there. You know, there's some references to tests that have been run, but then the results weren't logged very well.
Should make Simeon come back to you.
Frankly, we make everyone come back. I'll be emailing. Yeah, it's
So they just got the testing to the point of being ready to develop.
yeah, I think it was kind of in the proving of concept phase that this is a viable way to test this, and then now we're in the fleshing that out and actually putting numbers to it. This is how this is our success rate. This is roughly how it would work in space, which is a challenge because replicating space is hard on the ground. One pro of joining SI, Dr. Pernica buys you pizza and you get to hang out at his house and see his dogs.
Not offering pizza every time.
Well,
I'll take my dogs on this time. I don't know about pizza.
they're so nice. We should have put I have pictures of them. We should put it in the slides.
This opportunity. Okay, any other questions?
Thanks, Bart. Before everybody leaves, sooner or later, I'm gonna send out an email about an outreach event. Dr. Schmidt's looking for a couple guest lecturers for the 2790 Bloomsat class. So if you senior design people looking for outreach events, that'll hit your inboxes when I get around to it.